All right, so we're recording now. I think though I don't think you're on the recording because last night I was watching the recording and I didn't see anybody's picture on there, so I think you're all right. I don't know if you care, but all right. So this is I'm going to start off with hit the record button. So I guess I'll share the screen unless you had a question. Okay. All right. So share the screen. All right. And good. I'm glad you're there because there's something I want to share a screen later, and I want to see if it's a little video I took at the courtyard today, and I want to see if it make sure it's not a fiasco like the last time I tried to share one, and all it showed was a calendar. All right, so here's our announcements. Now I've changed this. I've changed the calendar again partly because of what we're doing here. We're doing the 4 to 5 live Zooms, so I put those in there. Those will be Monday, Tuesday, Wednesday, Thursday, but Friday I'm supposed to take that time off. So I won't do a live Zoom on Friday. I'll just do a wrap up Zoom like I used to do, and I'll post that by 1 o'clock Saturday. Okay, unless something weird happens. So it should be posted by 1 o'clock. The Fridays class. Okay. What else changed on this? Oh, I moved back I'm still having trouble getting a hold of a couple of kids virtually to have them take this test 1. I'm about to give them a 0, but I thought I'd give them another day. So that pushes it back to Thursday for the last day, thinking right now, which puts then I'm going to go ahead and get the tests because I got to wait till I grade those makeup tests. So by Sunday, all the test grades should be in. That means that Monday, Tuesday, Wednesday, Thursday next week would be black day, black and blue day. So I'd have the tests somehow for you guys, for virtual kids, in folders or in envelopes or something that has your name on it, so no one can see your stuff on the porch, I guess, like Sunday or Monday night. And you have 4 days to do it, turn it back into the hand-ins box if you want to get black and blue points back. All right, and then I've also changed it where I've changed the test. It's not a 200-point test, it's a 150-point test on Thursday the 19th of November, and it's just test 2A. We're not going to turn in the packet. I don't think we're going to finish the packet by then, so it'll just be like a mid-packet test. And then 2 is going to become a mega packet, and then it'll be another part of it coming out, and we'll turn all that in before Christmas. This is a nightmare of a semester. Also, these are the details of the week. Oh, hi. Hi, Sophia and IO has joined us. These are the details of the week. And I put on there I was telling Rose that we're doing the Zoom wrap-ups Monday, Tuesday, Wednesday, Thursday, but not Friday. Because Friday I'm not supposed to do physics after noon, as agreed to with Jamie. So I'll just do a wrap up on Friday sometime. It'll be out Saturday at 1, but it won't be a live Zoom. Okay. Also, just the handbags. Oh, by the way, I have a lot of your notebooks in those handbags. I take them out at night, but I put them back in when I get back home. So they're there right now. If you want your notes, and really, I think virtually, yeah, either way. The problem virtually is if you're turning in notebooks, I can get them back to you, but it's a whole hassle. I don't know. It'll work. It works. So last time I know Eric asked a question on this. I don't see him here, but he was asking a question about number 2 on this one. Number 1, remember we talked about this last night, but number 2, he was saying, well, I don't see I don't see an omega, but I put a couple hints on there that, think about a year, how long it takes the Earth to go around the sun, and how far it is in radians for a year. So hopefully that's enough to get you to figure that one out. We did this one last night. We're going to do 5 tomorrow. And then that all is due, that's still due tomorrow night at midnight, 2.5. All right, so today we concentrated on Galileo. And we did some pre-talk before the lab. Okay, so we did some talking about Galileo. Let me just give you a quick review of that. So let me set the scene. This is at 1605, and people back then believed in Aristotle. Aristotle, of course, was like 400 BC, but Aristotle wasn't obviously a physicist. He wasn't even a scientist. He was a philosopher. And so I don't blame Aristotle. He was an amazing philosopher, but he was a terrible, terrible physicist because he just kind of made stuff up. Well, that's what philosophy does, right? They don't get their hands dirty. So he philosophized about nature because he was a natural philosopher. And so the idea that here's some huge misconceptions that came out of Aristotle. One, that things fall to the ground at about the same rate, like they don't really accelerate. He also said that objects, when they go in the air, they go up, 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 and then turn around and come down. So he said that was the path that objects take, because he did philosophically, like a stone, like he said, things try and go back to their natural place. And so natural things do, like a stone is from earth. So when a stone is projected, it'll go to a point and then it'll turn around and come back, but it doesn't go in a projectile motion. And no one really questioned him about this. He said that one thing he said that seemed logical, I was dropping balls in class and stuff, but if I drop a basketball versus a tennis ball, a basketball has a mass of 550 grams. A tennis ball has a mass of 55 grams, most basketballs and tennis balls. So a basketball is 10 times the mass of a tennis ball. And so what Aristotle said was things that are more massive would fall in proportion to their mass. So a basketball should fall 10 times faster than a tennis ball to the ground. And so in class, I demonstrated dropping a basketball, dropping a tennis ball at the same time. And of course, they hit the ground at the exact same time. So what still floors me is that nobody questioned Aristotle. So for 2,000 years, all you had to do was go out and drop a rock and a boulder, and you would have seen that it's wrong. But no one really had, think of education back then, there weren't really like schools. So there were schools, but they were mostly for reading the Bible and for learning Latin and things like that. So it wasn't really, you didn't sit around and think about science. There was no science. So I don't blame people. It just seems weird that it took 2,000 years before Galileo finally said, this doesn't seem logical to me. And so Galileo got to thinking about it. He said, if I drop stuff off the Leaning Tower of Pisa, and he was into the idea of inertia and what that makes things do. He said, it doesn't make any sense that, he said, I propose that the two objects would hit at the same time. And apparently some Galileo's minions later on went and did it and showed that it was true. So he started to try to understand. He said, well, I can quantify this. Like I can put numbers to it. And so Galileo, the problem with it is we talked about this last night, how would Galileo time it? And it didn't have a watch, couldn't use a pendulum clock. That's what he invented. Later on, he didn't invent it. He thought about it, and his son actually built it along with Christian Huygens. But he uses pulse. He uses his heartbeat because that was a regular thing. So he uses heartbeat. But the problem is, if I drop, and I did it in class today, if I drop a ball from the ceiling in class and we all timed it, it only took 0.78 seconds to fall. Well, you can't even barely get one heartbeat out of that. So Galileo using his heartbeat to measure things falling to the ground doesn't work. So he said, okay, I will dilute gravity and I will roll, instead of dropping things, I will roll things down a ramp. And so he commissioned from Salviati, he said he's going to dilute gravity. So he commissioned to have various ramps built. And this is a later ramp of his. This has the bells and all, but earlier ramps. So the ramp started off fairly small. They got bigger and bigger. His biggest ramp was like 30, it was about 20 some odd cubits, it was about 30 feet. So outside today, we recreated Galileo's experiment. But instead of bells, though, we used PVC and holes. So I'm going to share that screen. I'll stop this sharing. And I'm going to see if, okay, do photos. Hold on, photos. And there's that video. I know you can't see it yet. Hold on. And now let me go to share that screen. Where's it at? Share screen. Oh, there it is. Okay. Okay, share it. Can you see that video? Good. Okay, so here's a little 1.5-minute video I took at lunch today. And this is in the courtyard. So here we are on the west lawn, and can you hear that okay? Yes? Okay. We're trying to recreate Galileo's experiment, and Galileo was trying to dilute gravity because he's trying to use his heartbeat. So he had a 30-foot ramp, and this is about a 30-foot ramp. It's on a ramp. It's a tube, but he had little bells. Okay, so we're not quite the same as his, but instead of using bells, we have holes. So we put a student, and I showed you pictures of this, but we put a student at each hole, put 2 or 3 students at each hole. We had one student drop the ball here and then started rolling. And then when the ball would hit the hole, the student would stop there. So everybody started their stopwatch at the same time. Then they would stop their stopwatch. So there's hole 3, there's hole 4, okay? And so every meter, we have a time of where the ball is. And then somebody grab it as it came out the back. It took us 2 or 3 trials to get this. Here we are. We're on the courtyard. It's a beautiful day, by the way. And yeah, we got pretty good data. And so I'm showing the data. I will include the data from, I think Third Hour had the best, so I'll probably include their data. Okay, I'm going to tear this thing apart. Okay, so let me stop that sharing and go back to sharing the screen. So I'm going to use Third Hour's data. All right, so that is here. All right, so write this data down. This should be on your sheet 2.6. I need somebody to make me another one, to make me I want to do 3-meter tubes. So we don't have it, because every time it hits a coupler, it always bounces, and that messes up our data. But this data was pretty good. Okay, so can you read that okay? And blow it up. So these are the seconds that it took the ball to get to each hole. All right, so when I wrote this sheet, we had a handicap ramp outside the science building, which was a little steeper. And so it didn't take as long. Well, this one is going to go over my graph a little bit, but it's okay. It worked out all right. So we're going to plot this now, and this will be X and then T. And for X, it's nicely worked out because there's 9 holes. And so these are meters. So, 2, 4, 6, 8. And these are meters. And then on time, you say, well, I'm going to just go every one being 1 second, but we need to be as detailed as possible. You'll see why tomorrow. But if I go time here, I'm going to go every other one. So 0, 1. I know I'll go off the graph. That's all right. 3, 5, 6, 7. And I can go out. And then if you look at the edge of your paper, you can go on out to about 8.5. And that's where we need to be, because that's our last time. So we'll go out to 8 and 9, or you can go to 8.5. All right, so then we got to plot our data. So 0, 0, of course. So I'll let you plot it, and I'll plot it quietly. It's something like that. About like that, eh? Oh, this not the way. Okay, something about like that. It's better. It's better. Okay, so don't connect dots. We never connect dots in physics. We're always looking for trends. Okay, you with me? Everybody with me? You know, I don't have, I don't have room, the space for chat. So you have to just say something if you turn your mic on and tell me to slow down or whatever. All right. So before we start to plot it, I want to go to the back, flip over to the back of the sheet. So before we, like I said, before we started plotting, we need to look at the patterns, the possible, like there's only so many ways that, there's only so many relationships. I mean, nature's paints with a broad brush. So the macroscopic relationships in kinematics are fairly simple. Okay, maybe not subatomically, maybe not in quantum world, but in macroscopic world that we live in, nature's relationships are fairly simple. All right, so we have these different orders, and some we've already done. So like for instance, first order relationships are just linear lines. And so the equation there is x equals vt plus x naught, right? The red equation. It could start at 0. It could have an initial position. It could have a lower slope. It could have a steeper slope. All of those are examples of first order relationships. Negative first order relationships are the same thing, only with a negative slope. So x equals negative vt plus x naught. So those are still linear, but negative sloped. Different examples. Oops, that's almost too flat. Back. Okay. Zero order relationships are really simple. Positive zero order relationships mean that nothing happened. You just stood still or you sat still. So in that case, it's x equals x naught. Negative zero order in the fourth quadrant, x equals negative x naught. Okay. Now, so that's really what we've been doing all year, driving me crazy. So let's kick it up a notch. positive second order now is the order tells you the power on the t. And so here we have x equals k t squared. Now, that k means k stands for a general constant. This is the k you learned in kindergarten. Just a little written k, not cursive. So I put this note, and we talked about this in class, because you got to be careful with your k's in here. So make it a lowercase printed k. Uppercase k stands for kinetic energy. Cursive lowercase k stands for spring constants, which is how stiff a spring is, like a car spring versus the spring in your ballpoint pen. Those are called spring constants, and there's whole tables and tables of these things. Capital K, which is cursive, is called a torsional constant, and that is how much twist can you put into a wire. So the point is that you got to be careful in physics with your uppercase, lowercase, cursive, not cursive. So this K here is a general constant. It's called a proportionality constant. We'll get back to that at the very end. All right, so we know that this is parabolic. So it looks like a bowl, right? It could start, it could have an X naught. It could start down here. It could start up here. It could be really wide open. The K could be like 1/5, or the K could be like 10, so really steep. So all those are considered second order relationships, meaning that the T is squared. Well, then obviously, what would third order be?
Cubed.
Yes. So X equals K. Now I put the same K on there, KT cubed. Once again, it's not the same K. K is a generalized constant. If I wanted to make it a specific K, I would say K sub 1. Or if I'm going to talk about another, so if I'm comparing two constant proportionality constants, I would say K sub 1 versus K sub 2. But if I just say K, it means general. All right, so this is cubic. What does a cubic function look like? Tell you the truth, in the first quadrant, it looks like a squared function. It looks like this, right? That's a cubic function. I can't tell the difference. So what we do is, we know it's not the same because a cubic function does this. Remember this from algebra. A squared function is a bowl. It does this. So you do need to, and I do take off if you don't on tests, if you're distinguishing between a third order and a second order, you've got to put that what's going on in the second and third quadrant. So there is a flatter one, but these are all those little saddles, you know. Okay, so that's the generalized graphs of third order relationships. So let's keep going back. If I look at this, I go, okay, that's third order, second order. This is like t to the first, right? So that's first order. Zero order, because t to the 0 is 1. So then what would this equation be? X equals k
t to -1.
Right, t to the negative first, which we know is 1 over t. So what would this graph look like though? What does that graph look like? And most people in class didn't know, so let's do a quick little t-chart. So let's say that k equals 1. Let's keep it simple. So then we have x equals 1 over t, right? If k equals 1. So if I said t was 0, I'd be in trouble. So let's go tx. So if t is 1, x is 1. If t is 2, x is, and then we'll go 3, and then I'll go 1/2, and then I'll go 1/3. What the? Oh, 1/3. Okay, so fill in the x's. I screwed up. I didn't get coffee. That's last night's coffee. Okay, so if t is 2, obviously x is 1/2, right? If t is 3, x is 1/3. If t is 1/2, x is 2. It's just the inverse, and then 3. So I come back over here, and when I plot that, I just sketch it. 1, 1, 2, 1/2, 3, 1/3. Okay, and then this way like that too. Okay, so it ends up looking like, now, what is the name of this function from algebra? What do we call that? It's an inverse relationship, I'll give you that. But it's a brain fart. I think in chemistry, it's not isotope. I've seen it all day today in class. I'm getting tired.
Asymptote?
Yeah, asymptote. But I don't know, I'm thinking isotope because chemistry. Acetope. Acetope. Yes. Now, in kinematics, that's not very common. It is sometimes like this. This is one of those things that the more you do, the smaller it gets. The one goes up, one goes down. The I mean, it's not a, it's also called an inverse relationship as opposed to a direct relationship. Yeah. Whatever. And then, but you know what I mean, is one goes up, the other goes down. So negative inverse would be look like that, fourth quadrant. But those two, I kind of discount because they don't really play a role in kinematics. They do play a role in physics, but not in kinematics. Oh, negative second order looks like this. Okay, and then negative third order looks like this. Okay, and that's x equals negative kt squared. And we'll come back to this all year long. I'll say, well, look, I'll say, no, kids, it's a third order relationship. You can't do this. And it also comes into play in calculus a lot. Negative kt cubed. Okay. And that's that would be x equals negative kt, the negative first. Okay, so pretty much all the things you've done today, all the movement you've done today can be captured in really these 8. It's really anything in these. If something happened today that wasn't in these, you probably would be in the hospital right now, because it'd be like this. This is most of your day right here. Those 6. You're sitting still. You're walking at a constant rate. You're accelerating. You're speeding up, or you're slowing down, whatever, or you're speeding up backwards. This is if you're like on a roller coaster, or if you're in a car and you punch the gas pedal, or you slam on your brakes, then you might be into a third order relationship. If you get into a fourth order relationship and the K is fairly high, then that breaks your bones. Fifth order would probably kill you. So with a K of 1 or greater and a fifth order relationship would end in death for most people. You just can't. Your body can't handle that. So most of your day is 0, first and second order, with occasionally third order. Somebody comes up and shoves you in the back. Hey, how you doing? That's third order. Or you trip and fall. That's third order. Okay. Now back to this. So the question we have now, we're getting close to being done. I promise. We're not going to go till 5 probably, unless you have questions. The question we have now is, what is this relationship? And when I look at it, I go, okay, I'm going to, let's say I decide that I take my ruler here and I'm going, well, I'm going to go best fit line. I've been taught that since 7th grade, so that sounds good to me. Well, what's wrong with that logically?
Aren't you missing the other points?
Yeah, you are. Yeah, you can't pick up all the points. My argument to you would be, Well, I can't pick up all the points anyway. I mean, you cannot do this. This is extremely egocentric. So you cannot do this. You cannot go pick up every point. That means that you did not make a mistake. That means you're saying there's no error. And there was error because the kids, the ball's rolling by their hole so fast. It's kind of like a mouse. You see a streak. You don't really see the ball. So it was sort of some people anticipated and they went too fast. We did enough trials and we tried to take the average. So this is a big no. You can never do that in my class, in any kind of science class. So if I say, well, you're not necessarily going to hit all the points, then I'm just going to make it linear. What's your argument against that?
It doesn't show acceleration.
Whoa, I think you're taking a giant leap. You're telling me it accelerated, but I want the data to tell me that. What's the only point on this graph we know is right?
The origin.
Right, 0, 0. So if I do this little best fit line thing, that will not work because I didn't go through the origin. So that's your killer argument that you cannot do that. You have to go through 0, 0. So if we have to go through 0, 0, now you have an argument. You can't do that circular reasoning. Well, I know it's accelerating. How do you know it's accelerating? So you can only say I know it's accelerating because my data tells me so. Now we're thinking like Galileo, right? Because Galileo, they're saying, hey, it's not accelerating. You can't tell us that. Aristotle didn't talk much about that. So, what are you going to be? You're going to believe Aristotle or are you going to believe your lying eyes? So we do, well, first off, okay. Here's a big concept. And this is the name of my book, my children's book I'm going to write. Look for this at your bookstore in 2025. And the book will be called Nature Paints. See, it's going to be a color book. Nature paints with a broad brush. And so, meaning that unless you're talking quantum or isotopes, or like quantum leaps inside atoms on a macroscopic scale, like the physics we live in. Like I said earlier, the relationships are fairly simple, and it is a broad brush stroke. So when you're plotting things, you do what is called, instead of a best fit line, we call these a smooth curve. We've established it cannot be linear. So it must be a smooth curve. Smooth curve. Okay. So now you got to do your best artistic shot at this. I'll go purple. And I would do it lightly in pencil at first. You got to go through 0, 0. So you come up and you don't go ziggy zaggy. You keep that broad brush going. So you come up. I don't like that. I'm gonna do it again. See, I get to do this. So still don't like it. My hand is sticking. You want to keep it smooth. That's better. It's not great. So once you have it the way you like it, you can kind of thicken it up. This is where that art comes in. The little kids are going to love it. We'll make it fun. Yeah. Okay. Getting tired, so I guess I'm gonna call it good. See, I hit most of the points. In other words, I honored my data. This is real data. I didn't make it up. We have on the room 807, there's a sign, there's a word that we've painted on top of the door, above the door, and it says Nullius in verba. It's Latin, and it was the motto of the Royal Society, which was headed by Newton. These are all the greatest thinkers in the world. And their motto on their crest says Nullius in verba, which means not by word of mouth, which means that they are truth seekers. So they're looking for truth. And so everything has to be verifiable. And that became, Galileo was, in my mind, the first scientist. There were astronomers. There was Kepler, there was Tycho Brahe, there was Copernicus. But as a pure scientist, somebody that's using data, Galileo had pages and pages and pages of data. You know what Galileo didn't have? He didn't have this. He did not have a graph. Graphs had not been invented yet. You guys ever heard of a guy named Rene Descartes? If you do philosophy, if you study philosophy, Rene Descartes, one of probably the top 10 philosophers in history. He was the French Isaac Newton. He was a little bit older than Isaac Newton, but he was after Galileo. So you ever heard of Cartesian coordinates? You know, XY axis. You ever heard of the XY axis? in algebra or in geometry, right? There's the XY axis. That came from Rene Descartes, the Frenchman in, I'm going to get my dates off a little bit, 1700, let's say, 1680, somewhere in there. About 50 years after Galileo could have used it. So Galileo did not have the benefit of a graph like we do. He had to come up with his relationships all by just staring at numbers till he was blue in the face. But we can now look at this and go, whoa, that is a second order relationship. And so Galileo, we're almost done. Galileo came up with this equation. And this is the first true physics equation ever written. He said, X is proportional to, and that little symbol looks like a fish, that's called proportional. So meaning that as one goes up, the other goes up or whatever. X is proportional to not t, but t squared. That was revolutionary. That started the ball rolling, so to speak, but that changed. That's why we walked on the moon. I mean, it's that equation that started everything. Now, you would think that there were ticker tape parades and fanfare. Galileo's figured it out. No, he was met with derision, silence, and mocking. Anytime a scientist comes up with, especially one person, comes up with a new paradigm, they don't expect a ticker tape parade. You're going to get mocked and laughed at. Okay, because people don't like to shift paradigms. So this was not very popular, this idea that something could change as a square of time. It seemed ludicrous. Well, Galileo met with a lot of, he was met with a lot of pushback on this, but he got the notice of some Danish, and the Danes, or the Dutch back then, were really good at glassworks. In fact, if you go to like Netherlands and stuff, even now, a lot of glass shops, a lot of glass making shops. So they had come across these different shapes, and I have this in class. I should have brought some home, but lenses. So I show the class all the lenses, and normally we pass them all around. They look at them. We can't do that now. But so they gave these to Galileo, these little lenses, convex, concave, triangular shaped. And they did funny things. They were like little oddities because you could put them over something and it'd make it bigger. Or make things smaller. And so Galileo became fascinated by these glasses and how they affected light. Now, he didn't understand the idea of refraction because that was Newton later on. But Galileo kind of set the stage for Newton. Okay, so we'll leave it at this. Galileo stopped doing this. If he had kept doing this, he might have invented calculus, which means if the Danes had not sent him that glass, but the thing is, because of the glass, he eventually invented the telescope. So I can't say that it set us back because it just set us in a different direction. Physics-wise, pure mathematical physics was set back. And calculus, like we reached a point, finally Newton invented it, Newton and Leibniz in late 1600s, like 80 years later, finally Newton invented calculus. But just think about this. If we had calculus 80 years before, we'd probably be on Mars now. But it is sort of, you can't really talk that way because Galileo did figure out the telescope. Okay. And the last thing he did those little lenses, and I'll do a presentation on it tomorrow. Those little lenses that they sent him, his genius was, he didn't invent the lenses, but he put them together, the concave and the convex, in a tube, and then looked out that tube. Now he was in Venice, and Venice had the Campanile, which it still does. It fell down 100 years ago, but they built it back up. But it's a big tall structure. It's taller than Leaning Tower of Pisa. I think it was about the tallest thing in Europe. And they did this so they could look out into the ocean because the Venetians were the leaders in merchandise, in imports and exports in the world. So they had a great navy. So they were always there was enemies out there. So Galileo put the glass, the convex concave lenses in there. Then you could adjust it some. That was part of his invention. And he showed it to the admirals, the people that were in charge of the Navy, and they fell in love with it because they could now see a ship. It only blew up the picture by 3 times, but it made something 3 times as big. So you could see a ship way out there on the horizon before anybody else would. And if someone's trying to attack Venice, they could fortify and be ready for them. So militaristic, Galileo was smart, right? He was buddies with the military. He was buddies with the church. He was a friend of the popes. So Galileo had all kinds of connections. He got in trouble later on, but up until now, everybody still loved him. Now, that's about to get him in trouble, which we'll talk about next time. And he almost went the way of Bruno. Bruno was burned to death at the stake because he went against the church. Bruno said that, he said, the earth kind of goes around the sun, not the other way around. The sun doesn't go around the earth. And the church said, okay, Bruno, take that back. You're wrong. And Bruno wasn't a scientist, so he was 1600. He could not really give evidence. And so he ended up burning at the stake. And they kept giving he was in prison for like a couple of years. They kept giving him chances. Said, Bruno, recant. He wouldn't do it. They even, when they tied him to the post and said, Bruno, can you just say you're wrong and the church is right? He said, I cannot. It's not the truth. I stand for the truth. And so they light the damn wood, burning all around him, and say, okay, Bruno, we'll rescue you. Just you're a good guy, Bruno. Just say that the church is right and you're wrong. He said, I will not. And he burned to death. Agony. So Galileo, of course, people all knew this. So they kept telling Galileo, because later on Galileo gets in trouble with the church too, and they're saying, we're going to do to you what you did to Bruno. But we'll get to that tomorrow. So as far as the physics goes, that's as far as Galileo got. Now he went under house arrest when he got older, and he went back to this and did some more work on it. But this was the huge leap. Now we still have the other 2 graphs to do, and that'll be also tomorrow or Thursday. We're going to get off on Galileo a little bit because I don't do much history, but I'm going to do a little bit of history on Galileo. And then we will, either tomorrow or Thursday, we will go do those other 2 graphs. And this will be our first trio. Okay, so now I've talked about at least as much as we said in class, and a little more. You guys always get a little more. Questions? Can you guys see me? Oh, okay. Well, you can't. When I do recording, you can't see me, but you guys can. Okay, cool. At least you can. All right. Any questions? I gave you a lot. But it's still better than me trying to wrap the whole thing up in one day. That's dumb. Okay, well, we're at, we got 15 minutes still before 5. There's no reason to go to 5 o'clock. We're done by 4:45. Let's be done.
Oh, I have a question.
Yes.
So
Let me turn this. Oh, go ahead.
okay, so on number 2 of the gold standard, when you said the omega of the Earth around the sun, is that like 2 pi over?
Right. Well, right. So omega, right. So for when something's going around the sun, the Earth going around the sun, it goes 2 pi radians, right? That's one complete revolution. How long does it take to do that?
365
Right.
days.
So we covered this last night. 365.25. You're gonna go leap year. Days, and that's really the crux of it. You know, the rest of it's. By the way, you don't really need that one. I think I was throwing in the 2 pi. Oh wait! Oh, stop! I was helping a kid at lunch on this, and really, you do need it if you say this. How many miles per hour? Okay, so we say V equals omega R, right? But really, we said V equals, we defined omega as delta theta over T times R. So you do need all 3 boxes. So in the first box would be delta theta, in the next box would be 1 over T, and the third box would be R. Okay, so you do need 3 boxes on that one. Okay? And then I think you can do the rest. Answers are on the back. And if you have questions on 1, 2, or 3, we'll do 5 tomorrow together. So we'll probably talk about Galileo and do 5. I don't know if we'll have much more time than that, but we'll see. All right, guys, I appreciate having an audience. It makes it much less lonely. I want to stop sharing. All right, then. Hey, look, voted here. So if you're 18, well, I don't know if you guys are 18. Go out and vote. Tell your parents to go vote. All right. Well, unless they're dumb. Don't tell them to vote if they're dumb. I know your parents are smart. All right. So only smart people vote. All right. I'll get myself in trouble. Okay. So I'm going to see you guys tomorrow, maybe. If not, okay. You'll see me on the recording. All right. Bye.